Hello, am I audible? Hello.
Yes, yes.
So you have already had one lecture, right? On number theory, possibly. So what I wanted to know at first is, so how many of you are from class? So I can see that 5 people have joined. How many of you are from class 11? I mean, you can come up individually and say that whether you are from class 11. Is there anyone from class 12 who's appearing for ISI entrance this year? No, right? And anyone from class 10 or below? So I'm assuming that all of you are from class 11, right? Okay. So what kind of exposure have you had to algebra before you joined up for this workshop? I mean, did you just go through the school material or did you prepare for Olympiads and stuff as well? Anyone?
Yes, as of me, I went through a bit of something that people like, something that's called abstract algebra. I'm pretty sure you're familiar with it, being an MSc student, I guess. I read up a bit on your resume.
Okay.
And
So you are currently in class 11, right?
no, I'm in class 12.
You're in class 12. So you will be appearing for ISI entrance this year, right?
Yeah, right.
Okay, good.
And a bit of linear algebra, and basically that's it.
Okay, no, I'm not talking about that. I mean, are you familiar with the ISI entrance syllabus? So if you have studied a bit of abstract algebra and linear algebra and all that, so you must be familiar with the ISI entrance syllabus as well. So that's what I wanted to know. A little bit of familiarity will help me actually, but that's not a problem here. You go through everything basically from the scratch. So 6 people have joined up. It's already 4:30. Let me start. Okay, is my screen visible to everyone?
Yes.
Okay. And have you all gone through the demo lecture note that I uploaded beforehand? It's available on the course webpage, I believe. Yes. And I left, possibly I gave 2 problems from 2 different topics over there, and I provided almost complete solutions. Okay, so there were a few question marks which I had left in the end, which I believe that you could solve, you could take it up from there. But anyhow.
Sorry, sir. What are we talking about now?
I'm talking about the demo lecture note that I uploaded in the class webpage. Have you gone through it?
I saw it, sir. Yeah.
Okay, cool. So did you find any problem or was the material clear? I mean, I tried to write it as clearly as possible. So
I think it was quite clear, yeah.
Okay, okay. So fine. So our target, so I will be teaching you polynomials today, which I personally feel is one of the most important topics that are asked in the exams. And this lecture will be essentially a continuation of whatever I had written down in the demo lecture notes. But if you have not gone through it, that's fine as well, because I will talk about everything in as much detail as possible. Okay, so what was our goal? It was to categorize all sorts of problems that categorize. Okay, so we have seen two categories so far. One is system of equations, and we had used the crucial technique of so how had we reduced the problem? We had essentially formed two polynomials, px and qx, and assuming that those polynomials are equal, we had compared their coefficients, right? That was how we had solved the problem. Okay, so this is a very crucial technique, and it uses something what who was it? Was it? Can you please come up and say who told me that he's familiar with a little bit of linear algebra?
Yeah, I said that.
Yeah. So can you tell me why this is true? I mean, I had even possibly left a question mark there. Did I? In the handout? If this holds for all x, that would imply a0 equal to b0, a1 equal to b1, all the way up to an equals to b1. So why is this true? This is a very person specific question. I'm asking to him only. If you
my guess would be we can arrange all the coefficients in a coefficient matrix, and we can arrange like both the coefficient matrices on both sides of the equality, and we can have x and x and all these unknowns or variables rather in like a variable matrix. So like something like yeah,
can do that, but what is the catch here? I mean, what will be the determinant of that matrix or something like that?
Sir,
yeah,
I used to think of in this manner that if there are infinitely many x for which this is true,
okay,
we can choose n plus 1 or n values of x that will lead to n equations, n linear equations, which are solvable, which have only one solution.
Exactly. So that's the point. Okay, so you're absolutely correct. So can you repeat it for the whole class so that the entire class can listen?
Take n different values for x, you will get n different linear equations, and by simultaneous solving method, you will find only one solution for this.
Right, n equations in n variables. So there exists only one unique solution, right?
I think it should be, I think I may be wrong. I think it should be 2n. There are 2n variables, right? So maybe 2n.
No. Okay, let me clarify this. You bring all the coefficients to this side. Okay.
Oh, yeah, absolutely. Then it's true.
And this holds for all x in R, right? So now can you say why this should be true?
Because you take an minus bn to be cn, ai
right,
to be
right.
cn.
A polynomial that is identically 0 for all x must have all its coefficients equal to 0.
Yeah.
That is a much simpler way to put it, right? Okay, so this property is actually called something called linear independence. Linear independence. Okay, so if you have a set of vectors, say this is very, I should not be talking about this in the very first class, but as one of you mentioned, if you consider this x power n minus 1 all the way up to 1, as a set of vectors, as a set of n plus 1. How many vectors? Sorry, this will be x. And this will be x power 1, this x power 1. So there are n plus 1. This is a vector of n plus 1 elements. If you consider it in that way, and if you take a linear combination of those vectors, this is a linear. What is a linear combination? Essentially, alpha 1, alpha I times x power I, where I runs from 0 to n. So this is a linear combination of vectors of the form x, vectors with elements of the form x power I multiplied by some constant coefficients, and the sum is taken over that. So this is 0 if and only if alpha I equal to 0 for all 0 less than equal to I less than equal to. This property is known as linear independence. Okay, and if you can find at least one alpha I not equal to 0 such that this still holds, then that is called linear dependence. So can you give me examples of two linearly dependent objects? I mean, two linearly dependent vectors. You can also, this is something like this is very abstract for you, I know, but have you heard of things like R2, R3, and so forth?
Yeah.
Right. So
A set of coplanar vectors.
right, essentially a set of coplanar vectors in R3 are linearly dependent, isn't it? So if you consider vectors like 1, 1, 1 and 2, 2, 2, these are basically coordinates. If you are not familiar with such matrix notations, you can treat it as 1, 1, 1 and 2, 2, 2. So this is linearly independent, right? What will be the constants that will multiply here? Alpha 1 and alpha 2 equal to 0 set. So if I take alpha 1 to be minus 2 and alpha 2 equal to 1, so that gives me 0, right? So I have found non-zero elements, so that non-zero coefficients, so that this linear combination gives me 0. Okay, so these two are linearly dependent. What about something like 1, 0, 0 and 0, 1, 0? Can you find alpha 1 and alpha 2 in this case such that this is 0 and alpha 1, alpha 2 not both 0?
No, I cannot.
Yes, you cannot. Right. So that is what I wanted to point out through this polynomial examples. Okay, so in this case, you can treat this n plus 1 element vector as something similar to what you know, which is r power n plus 1. Okay, and this can be proved that.
Can you please just elaborate on this one, like the r plus?
I mean, you can find a bijection. You can find a bijection from all polynomials of degree less than equal to n with your bona fide r power n plus 1. A 1-to-1 and onto mapping. Okay. And how do you find that bijection? Essentially take the coefficients, because the coefficients uniquely determine a polynomial. So if you have something like a0, a1 dot 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 an in r power n plus 1, you can bijectively map that with this polynomial an x power n plus an minus 1 x power n minus 1 a1x plus a0. Right? Because these set of coefficients uniquely determine this polynomial in Pn. So the structure of polynomials of degree less than equal to n can be conceived as something that is very similar to a vector of n plus 1 real numbers, or in layman's word, the n plus 1 coordinate. The coordinate with, the Cartesian hyperplane with n plus 1 coordinates. Okay, so this was a bit of a digression. I didn't want to get it. I regret getting into it in the first place. Let's move on. Okay, so okay. And the second technique that we learned, that is, what was it? It was the existence of roots, right? We will consider more examples of it, but we used a technique called intermediate value theorem to solve problems. So you see that polynomials essentially derive from a lot of different topics, from complex numbers, from trigonometry, from vector algebra, from calculus even. Okay. So this was crucially used. Okay, so now moving on. Now, the third thing that we'll study, which is the subject matter of today's lecture, it's called okay. So does anyone know what this means?
We can write a polynomial as product of two non-constant polynomials, so it is reducible as reducible.
Okay, so that means you think that x square minus 2, I can write it as x plus root 2 into x minus root 2. So x square minus 2 is reducible, right?
Over R.
For R, right? So that is the key point.
We need to consider irreducibility in what type of coefficients. We can consider irreducibility
Right.
for reals or integers.
You're right. So let us give a precise definition. So this is very common confusion while dealing with problems of irreducibility. Okay, so again, this is a very abstract algebraic topic. It plays a very crucial and fundamental role in abstract algebra in something called ring theory.
Sir, I am sorry to interrupt, but can you show me the first item that you?
Oh, the first item was system of equations.
Okay, thank you, sir.
So since we do not have any knowledge in that for the time being, we shall try to simplify every theorem of irreducibility into the language that we know of. Okay, so let's start off with a definition. So what is an definition? An irreducible polynomial is a polynomial cannot be factored into product of non-constant polynomials whose coefficients, all coefficients belong to the same set as that of the original. Okay, fine. Now, so we will use a notation here. Okay, so this will be our notation for this class. This means set of polynomials with coefficients. There is nothing to be scared about this f. I'll not talk in detail about what f can be, what f cannot be. For us, f will be whatever we know of. Our real numbers, complex numbers, integers, rationals, etc. Okay. Okay. So the first result that we'll consider irreducibility is something like suppose a polynomial. Let's say, let me give you a polynomial, maybe say x cubed minus anything, 2x minus 1. So this is a polynomial that belongs to zx, right? It also belongs to qx trivially. And you see that this polynomial, this will probably give you a reducible polynomial. I want something which is irreducible. Okay, so is this first question is this an irreducible, or maybe let me take a simpler example. We'll get into this example later. Let's take x square minus 2. This is irreducible in zx, right? And it is also irreducible in qx, isn't it? So can I say from here that polynomials which are irreducible in zx are also irreducible in qx? Is this statement true?
No, this may not be true.
Yeah, example?
Like if we take x minus half into x minus 3 by 2, that is
No,
irreducible in z.
Sorry? X
That will
minus
be
half into
x minus 3 by 2.
3 by 2. But how does that belong to zx? I mean, the coefficients are not integers, right?
Oh, okay, you mean the coefficients need to be
Yeah.
integers.
These polynomials I'm talking about here, they should belong to both. I mean, they should belong to zx. If they belong to zx, they automatically belong to qx.
If we can reduce it in Q, we can also reduce it in Z, because if we reduce
If we
it
can
in
reduce it in q, we can also reduce in z. But what about the opposite? Can we do that all the time? Think about the GCD of the coefficients. What should be restraint on the GCD of the coefficients so that irreducibility in zx and irreducibility in qx become equivalent?
GCD of all the coefficients should be 1.
Right. GCD of all the coefficients should be 1. Okay. So can you give me a quick example for the entire class to see that? I mean, how this is violated and when it might not hold? Or maybe let me write down a result for you at first. So this thing becomes more clear to you. This is called okay. Let me state the theorem for you. Okay. So Gauss lemma says that consider Qx and Zx. Let Px in Zx. Now, if Px is reducible in Qx, Px is reducible in Zx. Further, suppose the GCD of coefficients of Px is 1, then Px is irreducible in Zx if and only if. So you know the meaning of this, right? If and only if. It's a both ways implication. Yeah. Yes. Do you all know the meaning of if and only if?
Yes.
Okay. If and only if, so Px is irreducible in Qx. Okay. So let me sketch a proof of this, and then possibly why you will see that why this GCD condition is crucial.
I think I got a counter example.
Yeah, please go ahead.
If we take 2x square minus 7x plus 6.
2x square, lovely example. 2x square minus 7x plus 6. So this belongs to Zx. This is irreducible in Zx, I guess.
Yes.
But this is reducible in Qx.
Qx.
Right. Perfect. Okay. So we will. Shall I develop the proof, or maybe I should give you a problem or two first? Okay, we'll come back to the proof of Gauss's lemma, but let's develop the theory a little bit more. Okay, so that we can look at one or two repercussions of this lemma. Maybe here is a very silly result, I would say, or you would feel that this is silly at this moment. Okay, so let Px belong to Fx. And what is our F? Those, well, if I'm excluding Z for the time being. Okay, so I have RC. Okay. Then Px has a factor of degree 1 if and only if Px has a root in. Sounds silly, right? Isn't it? So if a polynomial has a factor of degree 1, then the factor must be of the form something like alpha x plus beta into some qx, that will be my px, if it has a factor of degree 1. Then clearly minus beta by alpha should be a root of this polynomial, isn't it? Okay, but we will look at this result from a slightly different angle. Okay, so suppose px has a factor of degree 1. Can we assume that the factor, I mean, the factor is of the form alpha x plus beta? Can we assume without loss of generality that alpha is equal to 1?
Yeah.
Yes, we can, right? So let me write the factor as something like x minus k. Okay. Okay. But then we have pk is equal to 0, trivially. What about the other side? Suppose pk equal to 0 is given to me. Okay, it has a root. It has a root in f. How do I show that it has a factor of degree 1? What do I use? What fundamental
Factor
result?
theorem.
Yeah, we can use more simply. I can say that we can use the division algorithm, right?
Yeah.
Right. Okay. So we will write this as something like x minus k into qx plus rx, right? But this is the remainder when you divide by x minus k. And from here, you can trivially see that rx must be equal to 0. I mean, rk must be equal to 0. Okay. All right. So, all right. Now, I mean, rx should be constant, right? Because the degree of the remainder is always at least 1 less than that of the thing you are dividing by, right? So I might as well write this as r instead of rx. So pk equal to r equal to c. Okay. So now another small result. It says polynomial of degree 2 or 3 in fx, where f is as defined above, is reducible if and only if it has a root in f. Okay, so this is very clear to you all, I suppose. I mean, a polynomial of degree 3, that can be, if it is reducible, then it has to be factored in something like a polynomial of degree 1 and a polynomial of degree 2, right? And for a polynomial of degree 2, it has to be factored into a two polynomials of degree 1. So now, by the previous result, we are done. And we can show that this has a root in it. Okay. So now can you tell me, so this is a problem. Yes.
We can use rational root theorem.
Right. I was going to develop this after going through
If
this
it is
example.
reducible, it must have a linear factor because
It
it's
must have a-
degrees t.
Right,
3 is 1 plus 2 or 2 plus 1.
right. So the others who have not got it, you don't need to worry, because here is a very intuitive result, which is called the rational root theorem. We'll come back to this problem, okay? No need to worry. So let Px equal to where is 0, again, arranging. So if now consider a rational number, say R by S, rational number where R and S, GCD of R and S is 1, relatively prime. And suppose R by S, that is P R by S equal to 0. That means R by S is a root of Px. Okay. Then R must divide the constant term, and S must divide the leading coefficient of. Okay. So who was it who answered me? Who answered this question?
My name is Ritabrata.
Okay, Rita brother. So can you go ahead and prove this?
Yeah.
Okay. So how do you do it?
We put x equal to p by q and we multiply both side by q to the power n, and we use division, I mean congruence.
Right. No. Okay. Let's not make it complicated. But idea, what you are putting ahead is essentially right. So you write, you have this. This is equal to 0, right? All right. So you multiply by, you get something multiplying by s power n on both sides. What you get is what will be the second last term? R s power n minus 1 plus b0 s power n. So that is 0, right? So now what you can do is you can simply write a r power n, you take all the other terms to this side, and you can take s common, right? From those terms. So this is an integer. So s must divide a in r power n, right? And we know that GCD s comma r, that is equal to 1. So this together implies that s must divide a. Fine. Okay. Similarly, now you can do another thing. You can take a0 s power n on the other side and take all the terms containing r, and you will get something here. And by a similar argument, you'll get that r divides. Okay. Now, So what can you say about monic polynomials from here? What can you say about monic polynomials?
All of the rational roots will in fact be integers.
Yes, has no roots that have non-integral parts. Okay, I mean all the rational roots are essentially integers. Okay. So now the rest of you, can you solve this problem? So use Gauss lemma. So since the GCD of all the coefficients is 1, reducibility in Zx and reducibility in Qx is equivalent. So now, again using this result, if a polynomial of degree 2 or 3 in fx is reducible, then it must have a root in f. So it must have a root in Qx, right? It must have a rational root. But so what are the only candidates for rational roots in this case? That divide 1 minus 1, right? I think the class is not following. So let me get back to the statement. What can you say about monic polynomials once again? Px has no roots in Q, isn't it? Because see, if the leading term coefficient is 1, then this must divide that, right? And what divides 1? 1 or minus 1? So the root must be integer. So now using that, what are the possible candidates? See, I know, suppose R by S is a root of this. Okay. Then by the rational root theorem, R must divide minus 1 and S must divide 1. So what are the possible options that I should consider as candidates for roots in this case? 1 and minus 1, right? There are no other options. Are you following?
Yes, yes.
Right. So 1 and minus 1 both give non-zero values when plugged into this polynomial. So this is irreducible. Okay. So another similar example, maybe trivial. What about this in Qx, let's say? Irreducible or reducible?
Is P a prime or what's P?
Yes, P a prime. P is a prime.
Then irreducible as nothing divides the prime other than the prime itself.
Right. So what are the candidates for its possible roots? P, minus P, 1 and minus 1, right?
Yeah.
Okay. So none of them satisfy this. Fine. Okay. Now we will move on to a more crucial result. Tell me whether you have seen this before. here is the result. Let Px be a polynomial with integer coefficients. Now we define something. What do we define? We define P prime x as not the derivative. We define P prime x as the image of Px in Z mod Pzx. I'll tell you what this is. So this is nothing but we are working with something like the coefficients reduced modulo P. Is the meaning of this thing clear to everyone? So if you have a polynomial a n x power n, a n minus 1 x power n minus 1 dot 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 a1 x plus a0, all we are doing is we are considering the remainders or the residues Rn when an is divided by p, when n minus 1 is divided by p, and so forth. And we are considering the new polynomial as nothing but Rn x power n plus Rn minus 1 x power n minus 1 dot dot dot. Okay. So is the definition of this clear to everyone?
Yeah.
Yeah. Okay. So moving on. Just a second. All right. So if Px not be factored in Zx, sorry, I'm writing it something. This should be P prime. See, P prime x cannot be factored in Z mod Pzx, then Px must be reduced. Okay. Why so? It's quite a strong result, right? I mean, if you, that means what does the contrapositive of this statement say? I mean, suppose what I want to say is that, so if you are given a problem where you need to check irreducibility of a polynomial with integer coefficients, and if you manage to reduce those integer coefficients modulo a certain prime number, okay, here p is a prime number, okay, or maybe, yeah, I should write p is a prime. Yeah. So if you reduce that modulo a prime number, okay, and if you see that that polynomial is irreducible, then you can straight away conclude that the original polynomial is Px is also irreducible. Do you get what I'm saying? So this reduces our checking of irreducibility in, I mean, I'm using this reducible and irreducible too many times. So this simplifies the problem of checking irreducibility of Px in Zx to checking irreducibility of P prime x in Z mod Pzx for some. right? Okay. So why is this true? A very trivial proof. I mean, there's nothing to prove. So if Px is equal to say Qx and Rx. So okay. So what I must say here is that let's proceed by contradiction. Okay. Proof by contradiction. Suppose Px cannot be factored in Z mod Zx, but Px is reducible in Zx. All right. So since it is reducible, there exists polynomials Qx and Rx with degree greater than or equal to 1, such that Px equal to Qx into Rx. All right. Now it's very simple. All you have to do, you reduce all the coefficients of Px modulo P. You get something like P prime x. You reduce all the coefficients of Qx modulo P. You get something like Q prime x. The degree does not change. You reduce this modulo P. You get something like Rx. So we have a factorization of P prime x in Z mod PZX. Clearly a contradiction, right? Is it clear to everyone?
The factor does not change with the assumption that the leading coefficient is always 1.
I'm saying the degree does not change.
Oh, sorry, the degree does not change with the assumption that the leading coefficient is 1 always.
Yeah, leading coefficient is not
Monic,
divisible by
that is.
P. Yeah,
Monic, that is.
monic.
Okay.
All right. So fine. So can you use this to show that this is what? I mean, reducible, irreducible, what? In, let's say, Zx?
With the rational root theorem, it seems not to be.
Yeah, definitely it is not, but can you use this result? Because this result will have deeper implications later on. So we should be familiar with this. And yeah, I should add that assumption here. I missed it, that P belong to Zx. Otherwise, as you can see that if the leading term coefficient is 0, I mean not 0, a multiple of P, then that will disappear, right?
Can we take a modulo of 3 and then say minus 2x cubed minus 2x plus 1 is indivisible, like, sorry, unfactorizable, irreducible?
This is just x cube plus x plus 1, right? When reduced modulo 3.
Yeah, but I was going the negative way.
All right, but how does it help? It will just bring out a constant factor outside. It will just bring out a constant factor of -2, isn't it?
Yes, but after that, if we take the -2 common and then we treat it like a monic polynomial, then the coefficient inside
Yeah, but
it.
the polynomial that you treat as a monic polynomial is essentially this, isn't it?
If I don't convert the 1 plus 1.
Oh, okay, okay. Yeah, you have the liberty to do that. Then go ahead. Yeah, then what you essentially have to do now, this must have a linear factor in Z mod 3ZX, right? So 0, 1, or 2 must be its roots. I mean, it must have a root in Z mod 3Z by this, which result? This, a polynomial of degree 2 or 3 in Fx, is reducible if and only if it has a root in F. So this is a polynomial of degree 3 in Z mod 3ZX. So it must have a root in Z mod 3Z. And what is Z mod 3Z? This is essentially the set 0, 1, 2, the all possible remainders when you divide by 3. Isn't it?
Yeah.
So now you plug in these values into this polynomial, and hopefully we'll see that none of them satisfy this polynomial. None of them are roots of this polynomial. Okay. Okay. So
Okay, right.
okay. Now let me ask you a question. Suppose I consider this polynomial x power 4 plus 1. And now I ask you a question. Suppose let's tweak this statement a little bit. So what will be the modified version of this statement? I want to see, suppose a polynomial p prime x is reducible in, this is a star mark. Okay. This is not a part of the result. Does this imply that p prime x is just the image of px? Okay. Does this imply that px is reducible in px? And the hint that I give you is this polynomial.
I think this one is reducible in modulus of 2. Like if we
Right.
convert,
How so? How is it reducible?
if we
in modulus?
convert the first coefficient to a -1, so like minus. So
No,
minus x
no,
for,
you are making a mistake. This result only applies to polynomials of degree 2 or 3, not more than 3. Because if you have a polynomial of degree more than 3, then you can factor it possibly into 2 polynomials which have degree more than 1. So if you are just checking 0 and 1, or more precisely, if you are just checking whether this polynomial when reduced has a linear factor, and if you fail to find the linear factor, that does not mean the polynomial is irreducible, right?
Can we express this polynomial in mod 2 and write it as x to the power 4 plus 4x cubed plus 6x squared plus 4x plus 1?
Lovely. This is the
So
way
that
to
will
do
just be expressed 1 here.
it. This is the way to do it, right? Why so? Because all these terms vanish when you take modulus of 2. You are just left with, right? And this is essentially x plus 1 whole power 4, isn't it? When you are considering modulo 2. So clearly this is reducible, right? So looking for linear factors is not enough when you have polynomials of degree more than 3. You should keep this in mind. This only works for polynomials of small degree, like 2 or 3. Okay.
I have a request. Could you please complete the reduction?
This reduction of this.
Yeah, into factors.
All right. I mean, what do you want to see? I'm not sure. This is just the binomial expansion of x plus 1 whole power 4. This is the
like,
factorization of.
We are trying to know if x to the power 4 plus 1 is reducible into factors of lower degree, right?
In Z mod 2 ZX. And what I'm trying to impress upon you is that
I see. Okay.
these two polynomials are equivalent. X power 4 plus 1 and x plus 1 whole power 4 are equivalent when we are dealing with modulus of 2. In the domain of modulus 2, these two polynomials are equivalent. So this polynomial is x squared plus 2x plus 1 into x squared plus 2x plus 1. Or anything, whatever you want, x plus 1 into x cubed plus 3x squared plus 3x plus 1. So this is reducible in the domain of mod 2. So does this imply that this is also reducible in ZX?
No, and that is actually the point we are arriving at, aren't we?
Yeah, possibly yes, but I don't want to go into. Are you talking about Eisenstein criterion?
I am hearing it for the first time.
Oh, okay, no. So you can do it by very elementary algebra. This, as you clearly pointed out, that this cannot have a linear factor, right? By the rational root theorem. I mean, the only linear factors it could have are 1 and -1, but they don't satisfy this equation. So it must, if it is reducible, we should be able to write it as something like ax squared plus bx plus c into cx squared. Sorry, dx squared plus ex plus f.
It
right?
factors into x square plus I into x square minus I.
No, but they are not a part of zx.
So it cannot be factored in zx.
I mean, why does that give you this idea? I mean, if it can be factored into, suppose you have a cubic equation which has 2 complex roots and 1 real root. Okay, so you can write that cubic equation as, say, z1 and z2 are complex numbers. I mean, z will suffice because the roots are conjugates, and we have 1 real root, say r. Monic polynomial. So what do you want to say? That since this factors into two polynomials with complex coefficients, this polynomial is not reducible.
No, because we are trying to factor it into quadratic, but the quadratic already becomes with complex.
Right. Yeah, that is a fair argument. So, but okay. What did you say the factorization was? I mean, you write this as minus I, right?
Yeah.
X square minus I into x square plus I. Okay, and you have something like ax square plus bx plus c into dx square plus bx plus c. All right. So you are provoking something called a very crucial result, that the factorization should be unique, isn't it? And it is indeed true. The factorization should indeed be unique. But okay, so yeah,
that's for fundamental theorem of algebra.
Right, that's fundamental theorem of algebra, but that does not apply outside the domain of Z. I should not. I should write maybe Z, C, and R, or whatever you have seen so far. Z mod PZ and you can even see that Z mod PZ, it does not apply this unique factorization thing, right? Because you had something like you can express a polynomial. Where did it go? In two completely different forms. So it might so happen that the unique factorization that you are relying upon, that does not always exist, but definitely. So if you are looking at this from the CX point of view, I mean polynomials with complex coefficients, then this holds good. I agree. But can we not go into that and perhaps try to provide a more algebraic answer to this? I mean, why such A, B, and C, D, E, F do not exist, such that this product is x power 4 plus 1?
We can equate coefficients.
Because you might have more difficult polynomials. So trying to get my point. I mean, this method is an essential one, because this you can just look and tell that this can be factorized into x square plus I into x square minus y. But there might be more complicated polynomials whose x cube has a very bad coefficient, x square has a very bad coefficient. How would you proceed in those cases? Isn't it? Suppose let me be more concrete, I guess. What about let me think of an example. Maybe this x square is show that irreducible over q. How would you proceed with such a problem? Can you find a quick complex factorization like you did for
No, that method is a bit complicated and it works not that good.
Right, that is not general. So this is the more general method that I'm trying to impose upon you. So if you have a polynomial of degree 4, and if you are sure, if rational root theorem guarantees that there is no linear factor, then you have to look at two polynomials. Since this is monic, I can assume A and D to be 1. So I have to look at two polynomials of this form, and I have to see whether their product is this. So please, I guess it would be a good exercise to pick up your pens at this moment and try to arrive at a contradiction in both of these problems. I'll give you, say, 5 to 10 minutes time. If you do this only, then you will appreciate the method that we will learn in some time. Has anyone arrived at a contradiction? Maybe I should write a bit. So let me do this. So suppose I can write this as x square plus x plus c into x square plus b plus d. Suppose. Okay, so I'm very bad at calculations. This should be a plus b x cube, and then I will have c plus d plus ab x square plus eb to x c. Am I right? So this is equal to x power 4 plus 1. So now what are the comparing coefficient methods? What does that tell you? That CD equal to 1. These are all 0. AD plus BC equal to 0. C plus D plus AB is equal to 0. A plus B equal to x. Sorry. 1. Alright. So now, can someone give me a contradiction from that? There are no real numbers A, B, I mean no integers A, B, C, and D that satisfy this system of equations. So see, again, system of equations is arising in such polynomial problems.
A plus B should be 0, right? Coefficient of x cube.
Plus B should be 0. I'm sorry. I'm so sorry.
Now we can check cases where C equal to D equal to 1 and C equal to D equal to minus 1. And from there we can get A also.
All right. So case bash is one of the way out. So you are saying that C equal to plus 1, D equal to plus 1?
When they are integers, if not integers, this won't work.
Yeah, these should be definitely integers because I'm looking at factorizations in ZX, right? So now you are saying that if we consider this case, then we'll get A plus B equal to 0, which does not contradict this, right? This goes through. And in this case, what we'll get that AB is equal to minus 2. From here, we will possibly get a contradiction because we have 2 minus 1, 2.
Yeah.
Yes.
And similarly, we will get a contradiction from this case as well. I'm not then possibly it will be a waste of time to look into this problem. Oh no, it will be a good exercise to look into this. You should. So again, assume that yeah. So how would you go about this problem? Similar manner or something else? You suggest something else. And this, I'm looking at irreducibility in QX. Right? It is equivalent because GCD is one of the coefficients.
So check in ZX.
Sorry. Yeah, checking ZX. Yeah, sure.
And rational root theorem will work because 1 is here. So root should be plus 1 or minus 1. And it's also monic.
Again, you are making mistakes. This is a polynomial of degree greater than 3. So it might have 2 quadratic factors, right?
Oh yeah, sorry.
I think the method that we used for the last problem, I think
That will work. That will
yeah.
go through, but here is a very prototypical method. See, this is in the previous case as well, you could apply this trick. I should have told you before, but notice that if I'll say px maybe is a factor of this polynomial. Okay. Then is p minus x also a factor of this polynomial?
So one thing I can say is this, that I can replace, like, take y equal to x squared.
You can take y equal to x squared, and then what will you do? So this
I'll
is
write the polynomial as y square minus y plus 1.
right. So this has no root by the rational root theorem.
I was more of thinking like x square minus x plus 1, right? Not 12.
Plus 1. This is 1. Plus 1. Yeah.
So x square minus x. So that is x minus half
Y-
whole square. X minus half whole square plus 3/4. So I have what I have done is I factorized it to two complex quadratics.
You have factorized it into two complex quadratics. Okay, so again you are invoking unique factorization theorem, right?
Oh, okay. So
Right. So I want to avoid that for the time being.
okay.
So is this true that if px is a root factor of this polynomial, then p of minus x should also be a factor?
It should be true.
Yeah,
It
P is even polynomial.
Right, even. Okay. So suppose, we will go by this method only, that what he suggested, substitute y equal to x square. And now we will try to write it as something like y plus a into y plus b. Okay. So we can show that this is irreducible by we can find. I mean, this is guaranteed by the rational root theorem, so there is no need to do this. But by this result, if we have something like x squared plus ax plus b as a factor, then x squared minus ax plus b would also be a factor, isn't it? Right?
Yeah.
Okay. So now what do you get? See, b squared is equal to 1, right? Or let me just maybe, what does it give? X power 4 plus the coefficient of a x cubed should be 0. What should be the coefficient of x squared? That should be 2b minus a squared times x squared plus b squared, right? That should be equal to x4 minus x squared plus 1. This will give me 2b minus a square equal to minus 1. So now there is a very easy contradiction from here. So this was the observation that I was trying to make you see. Okay, so now this problem is very simple, right? Because you know b square equal to 1. So once you will put b equal to 1, once you will put b equal to minus 1. In either case, in the first case you will get a square equal to minus 1. And the second case, you will get x square equal to 3. Right?
Why did we assume that the factorization has to occur in the form of x square plus ax plus b and x square minus x plus b?
Because you just said and you just observed that if px is a factor, then p of minus x is also a factor. Factor, I was not talking about roots. This is a
Okay,
very
okay, all right, great.
Yeah.
Fine.
Okay. So from here we get a contradiction because a cannot be an integer. Phew. Okay, so fine. Good progress. But now comes something that is invaluable while examining irreducibility of polynomials. It is the famous, not Einstein. Everyone mistakes it for Einstein. It is actually Eisenstein. Right. Anyone has any idea regarding what this is about?
Yeah.
Can you state the result for me?
If there is a prime P such that P divides all the coefficient except the leading coefficient and
Okay, so
And that
let's
P
find the
squared doesn't
polynomial.
divide in
Polynomial is a n x power n. Just a second, I'll let you go. But okay, now what are your assumptions? P
there is a p such that p squared doesn't divide a naught and p doesn't divide n.
P does not divide any. And anything
And
else?
p divides all the rest of the coefficients.
All the rest of the coefficients, right? So
If-
a minus 2, a minus 3, all the way up to a1.
If such prime exists, then p must be reducible over z.
Then px is okay. I should mention that these are all integers. Then px is irreducible. Fine. Okay. So is the theorem clear to everyone? I mean, there is nothing in the statement. It's just 3 assumptions and a result. But do you see that it can be used, how it can be used, or how it can be a powerful weapon for us while solving irreducibility problems?
But I don't get the intuition. Like, how is this true?
Okay, so let us see why is this true. That will probably provide you with some intuition. Yeah, this is like something that is very random is going on here, right? Because p squared does not divide a naught, p does not divide a, divides all the other coefficients. Okay. Suppose this does not hold. Okay, suppose again we'll see a quick proof by contradiction. Okay, so now I'll pose some questions for you to answer. Is a naught a1 dot 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 n, can I assume without loss of generality that a naught a1 dot 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 n have no common prime factor? I can write, or let me
If they have, I'll take them out as a
I'll-
constant term.
right, precise. I'll take them out. So without loss of generality, we can assume. Okay. Now, since I am proceeding by contradiction, let me assume that px has a factorization of the form, say ax into bx. All right. Now, suppose ax, say degree of x is equal to some r, which is strictly less than n, and which must be greater than or equal to 1, right? So what should be degree of bx? It
N
should be n
minus r.
r. Let's call it s for the time. So what do I have? R plus s equal to. All right. Okay. Ax, I write ax as, say, r power x power r, r minus 1, x power r minus 1, dot dot dot, a1x plus ez. And I write bx as dr x power
Shouldn't
r.
we use some other variable for the coefficients of ax, because we are already using them for px, I guess.
Oh, okay. Yes, sorry. Since I used capital A for this, I got carried away. Let me change the coefficients of this original polynomial. Maybe I'll change it to cx. Okay, solves the problem. All right. So can you write, say, okay, so see one thing that does P divide C naught? I mean, P divide C naught. I mean, sorry, what I wanted to say is that, see, observe that C naught is equal to A naught B naught, right? Isn't it? Px equal to Ax into Bx. So I'm just comparing the constant terms on both the sides. Is this clear to everyone? Why C is equal to A naught B naught?
Yes.
Okay, so I can say that P divides A naught or P divides B naught. Can I?
Yeah.
Right. Without loss of generality. So P cannot divide both, right? Unless A naught or B naught are both one. Okay.
Yeah.
Without loss of generality, let us assume that P does not divide B. Okay. All right. Now, I want you to express Ck, which is the coefficient corresponding to the term x power k in the polynomial Px, as product and sums of AKs and BKs, AIs and BJs, let's say.
Ck equal to summation ai bj where I plus j equal to k.
Right. Ck is equal to A naught BK, A1 BK minus 1, dot dot dot, AK, B naught. Right? So can I say that P divides AK for all k in 0, 1, dot 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 r? Can I say this? Think.
Yeah, we can show this by induction.
Right.
From P divides A naught with C1, C2, we can go further.
Right. We can write down C1, we can write down C2, and so forth. Right? All right. So this is induction. Right? So now P divides all the coefficients of Ax, isn't it? All coefficients of Ax. So P divides Ck for all k in 0, 1, dot 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 n. Is this clear?
Yeah,
So this is a contradiction.
right.
Right. That means our original polynomial, if it satisfies these conditions, then, but I should write down that P does not divide n. We know that by assumption. Hence, Px must be irreducible. Right? Okay, I mean, it will become more clear if we apply this Eisenstein criterion on some problems.
Can we apply this to the previous one?
X power 4 plus 1.
Yeah.
Can you?
We can apply it on P of x plus 1.
Right.
P
Right.
for, and we take
Let's
P equal
go.
to 2.
We'll come to that example. But for the rest of the class who are not familiar with this Eisenstein criterion, let us see the repercussion of this Eisenstein criterion at first. So, abiding by this, so there can be several polynomials that abide by this condition, right? I mean, look at a polynomial, say x power 7 plus 21x power 5, maybe 14. Let's go with something else. 6 x power 4, maybe 9x cubed plus 1. Say if someone asks you that is this polynomial irreducible or reducible, then you have a one-line answer to this. Isn't it? Can you tell me why? I mean, the people who know, please let the others speak.
Do we consider mod 3?
Right. We can see that P divides all the coefficients apart from the leading term coefficient and the coefficient with constant. The constant is 1 in this case. So you see that this is a very profound result, I should say. That gives you a very handy tool to deal with polynomials of any possible degree if they abide by 3 restrictions. If you can find a P that abides by 3 restrictions, then you are done. Okay. Now
I have a
let's come-
doubt with the statement of the Eisenstein's criterion. Can you scroll up a little bit?
Yeah.
Okay, so we are working for the prime P. It is given that P squared must not divide A0 and P must not divide AN.
Right.
So does it will it hold if P divides A0 but P squared does not divide AN?
No, it will not hold. Possibly you can try and find a simple contradiction. So you are saying that P
Suppose
P
A0 is
divides
such that P divides A0 but P squared does not divide A0. In that
Yeah,
case,
if-
can
if
Eisenstein's
it is
criterion
0,
work?
No, it might not work. I mean, definitely it can work. This is allowed. This is permissible, right? P can divide A0. We have used that fact. Without loss of generality, we assume. I mean, sorry.
Yes, right.
Here we assumed C0. There is an abuse of notation here. I should change all this to C0. See, I'm sorry. I made a very silly mistake in this statement. This should be all the way up to A0. Okay. I mean,
Yes,
it's a
yes,
part
we
of
should
the-
divide A0 also.
Right. We used that crucially in the proof, didn't we? So I should have written A0 here. No one pointed out. People who knew. Okay. You can live with that.
And it will start from AN minus 1
It will start from AN minus
or
1.
CN minus 1.
Right. CN minus 1. You're right. CN minus 2 all the way up to C. Good.
So here can we apply it? Like it is not dividing 1. 3 is not dividing 1.
Yeah, definitely we can apply
That is
it.
why I
That
had
is the
asked the
point.
question.
That is the point of this problem. So you can see that in very complicated looking polynomials where irreducible, the problem of irreducibility seems very evasive. You can apply Eisenstein criteria to simplify it.
No, I
So
meant
almost-
for this polynomial, we are considering the prime P 3. But
Yeah.
according to the Eisenstein's criterion, 3 should divide the constant term, but 3 squared can't divide the constant term. Here, a
Yes,
constant
yes,
term is
that was
1,
what
so
I was
3
telling.
does not divide 1. So
Okay,
Can
so
we use
my
3 for this?
assumptions are,
Can you state the
equal-
assumptions once more?
sorry. Yeah, so I should maybe include 3 here if I want to apply Eisenstein criteria.
In the constant
In
term.
the leading term or the constant?
Sorry. You are saying that, sorry, I should write 3 here.
Yes,
I mean,
yes.
all these terms 3 should divide, and P should not divide this term. So having 2 here or 4 here is perfectly fine. But I cannot have 9 here.
Okay,
Yes.
yeah,
Okay.
that makes it clear.
Yeah. Right. Now we can apply Eisenstein criteria. Right. You are. Okay. So for very so we can see that this has very interesting applications. So here's another one that that the point that came up some time back. Px is equal to x power 4 plus 1. How do you apply Eisenstein criterion? There is no such prime that will, I mean, the first thing that you look at is the constant term is 1, so no prime divides 1. So how do you apply Eisenstein criterion to this? I mean, the people who know, please don't respond. Let the others think about it. Is there any way that can you think of anything?
No prime divides x to the power 4's coefficient, but at the same time, like no prime square or prime.
Yeah.
So
So
no.
I should go back to this difficult looking problem and maybe no. Let's leave it alone. This is a much simpler example to explore. Yeah, go ahead. What were you saying?
Yeah, so no prime divides the coefficient of x to the power 4, but at the same time, no prime divides the constant term as well. So I don't
So
think it's
apparently Eisenstein criteria is not applicable, isn't it?
Yeah.
And someone who answered this question a few moments back, is it applicable?
Yeah.
Yeah, right. So why is it? Can you tell the class why we can apply Eisenstein criteria even to those problems where at the first glance it will seem that it is not applicable?
P of x is irreducible if and only if P of x is reducible if and only if P of x plus k is reducible for all integers k.
Reducible if and only if P of x plus 1 is or x plus k is irreducible.
And here we can take k equal to 1 and we can see we can expand P of x plus 1, that x plus 1 whole to the power 4 in binomial and take p equal to 2.
But just a second, is this statement clear to everyone? Because this is if x varies over all real numbers, so does x plus k, right? This is bijection with this.
We are just shifting the origin.
Yeah, sorry.
We are just shifting the origin a little
Right,
bit,
we are
so it
just
won't-
shifting the origin. We are doing nothing else. So irreducibility is not affected by shifting the origin, isn't it?
Yeah.
Okay. All right. So go ahead. Now we will look at px plus 1. What is that? Can you quickly tell me? Are you all familiar with binomial expansions? Because some of you told me that you were in class 11, right? So there might be some people who do not know how to. Am I right in assuming so that some people are not familiar with binomial expansions? If you don't know, then tell me. Otherwise, I will probably assume that you know. Okay, so everyone knows. Fine. Okay. Now this is x power 4.
And we can use the prime.
Sorry.
We can use p equals 2 to apply Eisenstein's criterion.
We can use the prime 2. So yes, once again, my mistake is being pointed out here. So we need the constant term to be divisible by 2 in order to apply Eisenstein criterion, isn't it? Okay. And make sure that if you are taking down notes, then you change all this. There was a terrible abuse of notation here. I should change everything to C naught. So whenever you are dealing with coefficients of this original polynomial, you should write down C i's in your notes. And when you are dealing with this polynomial ax, you should write down ax. Okay, this is our convention. Okay. So here is another example that that is always given whenever Eisenstein criterion is stated. This example is always given. It has a very specific name. This is called a cyclotomic polynomial, which has very interesting applications in the study of algebra. This can be written down as x power p minus 1. Okay, p is a prime. What about this? What can we say? Eisenstein, maybe?
What's the question again?
Is this reducible or irreducible? P is any arbitrary prime.
Irreducible. Take the prime to be p and phi of px plus 1.
Right. What do you get? Now what do? You can't go on expanding all.
We can use the
We
GP
can use
formula.
the GP formula.
Right. Right. What would that give me? X plus 1 power p, I guess. P. There are p terms. Minus 1 by x plus 1 minus 1, which is x plus 1 power p minus 1 by x. Now, this is a binomial expansion, and the constant term of the binomial expansion will get cancelled out. Okay, so that would leave us x power p minus 1 plus p into x power p minus 2 plus p choose 2 into x power p minus 3 all the way up to p choose 2 into x plus p. Right? Now see, Eisenstein criteria is applicable. Isn't it? Yes? Is it obvious to everyone that Eisenstein criteria can now be applied?
Yes.
Yes, we can use the prime P.
So you know this result, right? That P divides P choose K, where K is less than P.
Yeah.
Fine. All right. Perhaps one last example of this, then we'll be moving on. Tx is equal to 21 x power 5 minus 6 x power 4 plus 9x cubed plus 3x squared minus 15x plus 1. Okay, let me see whether I have assigned the coefficients correctly or not. Have I? So this is very similar to what I was writing down previously, right? This
If
is
you
what
want Eisenstein, then the constant term has to be.
right. See. What I made a small mistake while writing down this, right? I wrote down 3 here, and I wrote down 1 here. So at that time I didn't tell you, but what should I do in this case? This problem is very similar in essence to this one, right? See, all the terms are divisible by 3 apart from the constant term. What do we do?
Should we look at the reciprocal polynomial, like change x by 1 by x? Will that
Now
work?
we will look at the reciprocal polynomial. So substitute x equal to 1 by y. What do we get? 1 by y. Go ahead, tell me. I mean, maybe it will be more instructive to look at something like this, right? Y power 5 into p of 1 by y. What is this? Can anyone tell me?
X to the power 5 minus 15x. I mean, the powers are just reversed.
Right. So x power 5. Does everyone see it? I mean, I'm getting only 2 or 3 responses, so I need to ascertain that everyone gets whatever I'm saying. Sorry, I wrote down y. Right. Now, can you apply Eisenstein to this polynomial? Call this polynomial, say qy. So you can apply Eisenstein to this polynomial.
Yes, P equals 3.
Right. So now, the one who first answered me, who answered this question, I cannot see your names actually, so I have to call you by ones and twos, but it's very sad, but okay. So can you tell me that why does this guarantee, why does the irreducibility of qy irreducible implies px irreducible?
Because if P was reducible, we would get a factorization for Q, I guess.
Okay. And what would we write that? if we had degree of Ax equal to A and degree of Bx equal to B, then what would we have? Px is equal to sorry, I should write y to the power 5 p of 1 by y could then have been written as y to the power a of 1 by y to the power b of 1 by 1. So this is a factorization of qi. Contradiction. Clear? Can you see that these are both this will be both polynomials of degree A, and this is a polynomial of degree B.
Yeah.
Okay. Fine. The last bit of theory that we will do is something called Perron's criterion. Possibly we will just do it and we'll look at a very crucial and well-known application of this, and then that will be the end of today's class. So what does Perron's criterion say? Let Px be a monic polynomial. Okay. A1x plus A0. Okay. Okay. Now we have again a very weird restriction on these ends. Okay. This is the restriction. Assume that Px strange, right? Pretty strange. Okay. So I will provide a proof of this, but it will be too late if I begin it now. It's quite a long proof, but perhaps we will look at an application of this. Okay, the problem is, consider the polynomial Px, which is 5x power n minus 1 plus n is arbitrary. Okay, definitely greater than 1. Okay, n greater than 1. Is this reducible?
By Perron's criterion, no.
Right, by Perron's criterion. And this is a problem that appeared in. Okay, that's why I told that this is a very well-known problem. And it is reduced to a 1, but unfortunately, when the problem came out and Perron's criterion was not that famous. It was there somewhere in the vicinity, but people were not aware of it. Okay, so they had to do a lot of work.
So without Perron's criterion, this would be a
It
good
will be
Olympiad
pretty
problem.
difficult. I mean, you have to develop the proof along the lines of the proof of Perron's criterion, and this proof uses complex numbers.
Oh, I see.
So almost whatever I wanted to say, I have more or less the theory is covered. Next day, so today we were basically looking at divisibility and such things. Divisible by, I mean, reducing modulo some prime, looking at whether P divides the coefficients, and so forth. Next day we'll focus, and that will be the last of our discussion. It will not take a long time, just a small discussion with few problems. We will look at how absolute values, that is modulus or moduli of roots, real or complex. I mean, I should write complex, that includes real. So can be used to determine irreducibility. So this is our agenda for the next day, and we will look at the two remaining classifications of polynomial problems, which are roots of unity, and again, this is somewhat related to whatever we have seen for divisibility by integers. And possibly, if time permits, we'll look at some. Okay, we'll see that. We'll look at
What
lots
is
of
meant by divisibility of integers in this case?
divisibility by integers. I mean, which
Yeah, divisibility by integers.
I'm saying that suppose you have a polynomial px with integer coefficients, then here is a crucial observation that p of, suppose you have two integers a and b, then something like,
So if p is an integer polynomial, then a minus b will divide p of a minus b. Right.
look at such things and problems that arise out of it. Okay. All right. So the last question I want to pose for you in this class before departing is that we have been talking mostly about zx and qx, right? Not much about rx and cx. In cx, it is useless to talk about irreducibility. Why so? All polynomials are reducible, right? I mean, all polynomials of degree greater than or equal to 2. Isn't it?
Yeah, they will either have real or complex roots, so it will always work.
Right, it will always work. So in CX, that's why we did not talk about CX much today. What about RX? For 1 and 2, I leave out 1 and 2. What about greater than or equal to 3? I will tell you one subcase, and I will let you think about the other subcase over the period of the next 2 days. For odd numbers, I mean, this is obviously I'm talking about the degrees, okay?
For odd degree, it has real root.
Always reducible. Reducible, right? So the question I am going to pose for odd numbers greater than or equal to 3. And what about even numbers greater than or equal to 4? Okay. That's it, right? You can show that this is true. All right. But it requires a little proof. It's very intuitive as well. But suppose consider a quadratic polynomial that has 4 complex roots, then we will have something like x minus z1 into x minus z2 into x minus z1 conjugate into x minus z2 conjugate. So you can pair this up, you have a factorization. This is reducible. But can you come up with a sketch of a proof or maybe a motivation behind why this should be true? So on this note, okay, this is all for today's class. I will prepare a handwritten note possibly by today regarding at least I'll briefly mention all the topics that we have covered. I will also mention the problems that we have covered, and I'll add some supplementary problems to that. All right. Okay.
If we have any doubt, how can we ask
I'm
you?
in the WhatsApp group. I've been added in the WhatsApp.
Okay. I don't know your number actually.
Okay, so I was very recently added, like just before the class. So you can find it that Orgo sir added. Okay.
Okay.
Yeah, and so the last thing that I wanted to ask is that a little non-academic, but are you all ISI aspirants? Is there anyone who is preparing for CMI?
Yeah.
Okay,
Yes,
so
I will appear for
and
CMA.
anyone who is absolutely certain that he or she wants to join ISI Kolkata? I mean, provided that he or she clears the entrance.
Yeah.
Okay,
Yes.
that's good. That's good. +1 for you guys. Okay, then that's it for today's class. I'll see you on.
And I had a question.
Go ahead.
So, how many? Like we learned 2 criterions today. That is the Eisenstein's criterion and the Perron's criterion. And from what I've heard, ISI is actually very strict about applying.
Yeah,
advanced
that's why
theorems.
I will give you sketches of proofs, right? I mean,
Okay.
you won't
So
use
I mean,
them
if I need to apply these theorems, these
Yeah.
criterions in the exam, so do I need to write
you
out the
should
whole
at least
proof?
be able to write down the sketch of the proof, not even the whole proof, because if they see that you genuinely know the theorem and have applied it, then chances are that they will not deduct any points, but in the interview they will ask you regarding the theorem that you have used, and then you have to provide a complete proof there. Okay, and if there is no interview, then see, they will give problems mostly. Eisenstein knows that people know Eisenstein because it's there in Excursion even. So Excursion is a handbook that even ISI, the professors of ISI, the paper setters also follow. Okay, so they know that Eisenstein is a widely used thing. It's like Cauchy-Schwarz inequality. Okay, so you don't need to sketch a proof of that. But if you use techniques like Perron's criterion, then I mean the proofs. If you know the criterion, then you should have some idea about the proof. That's all I say demands. Okay, so maybe if you find time, you can write down almost something that indicates that you know the proof. Not maybe a rigorous long two pages proof, but at least a sketch that you know. Okay, because in the past people have used things like Jensen, Karamata, even in combinatorics they've used things like Ramsey numbers. But at least you have to show the examiner or whosoever is checking the copy that you have not marked it up. You know what it is about and how it counts. Okay. Is it clear?
Yeah, thank you.
Okay. Thank you then. Bye-bye.